Here's one more example of volumes by slicing. And here we're going to get to one of the standard things that appears in all the books is an object of revolution. And what we're going to find is it's a case where we have an object that has a hole in the middle, and when we slice it, we're not going to get a disc, but we're going to get what you would call a washer, like the thing you put in plumbing. Why would you have such a thing? Well, a napkin ring is a good example. It's not something we necessarily make a lot of, but it's just a nice, say a nice kind of round piece of wood with a hole in the middle to put the napkin, and it's going to be like varnished and very pretty and all that kind of stuff. But the main thing is that it's this somewhat cylindrical object. They're often kind of bowed out a little bit to make them look more pleasant, and there's a hole drilled through. And I'm going to make it a little more interesting is it's not just going to be a cylindrical hole. I try to make it very subtle that this has actually got a little bit of a curve as well. So it's kind of, the hole kind of flares out and gets wider at the ends and is a little bit more narrow in the middle. So one of the things I think with volumes of revolution that people get confused by or don't like a lot is how they're described. And we tend to have them as you take some sort of object, some sort of area in 2 dimensions, and then revolve it around an axis to get a 3-dimensional object. And I think what you want to think about is not so much that you start with the 2-dimensional object and you revolve it to create the 3-dimensional. It's the 3-dimensional thing is what you want to talk about, but if it's an object of revolution, then it's the same in all directions perpendicular to an axis, and you can describe it fully by taking a slice including that axis, like here the slicing with the plane of the board, drawing a 2-dimensional object, and then say it's what you get by revolving that. So it's really a useful thing. You want to describe something in 3 dimensions, that's tricky and somewhat difficult sometimes, but you can get away with a 2-dimensional picture. So going from the 3D object to the 2D is you take a slice, and in fact we're just going to have to take like half of the slice, the upper half, this bit here, and say it's what you would get by revolving that around an axis. So there's sort of going from here to here is revolution, going from here to here is slicing. Okay, so here's how you would see a specification of this. Somebody who does this stuff for a living would know that they just have to say, okay, what is the upper curve that's going to get revolved into the outer shell, the outer part of the wood, and then what is the lower curve, slightly less curves is the way I'm going to describe it here, to revolve around to get the inside, the edge of the hole. It's going to have flat faces here and here, just to be simple. Okay, so here's what they're going to do. They want this to be something where from the middle to the edge, notice there's going to be some symmetry here in our description. Why not? Why not use some symmetry? It's going to be 20 millimeters. Also 20 millimeters is going to be up to here, so this is going to be y equals 20. Here is going to be y equals 15. It's going to flare a little bit so that this is going to be y equals 16 millimeters, and this is going to curve down a little bit, so this is going to be y equals 18 millimeters. And it's going to be symmetrical over here, 16, 18, and this is where x equals minus 20. Okay, so if we want to suggest a little bit more the 3-dimensional object that we've got here, we can take this picture and we can simulate revolving, and that's easy to do. Whenever you have a 2D picture of some region that you want to revolve, just reflect it to get where the slice would intersect it again, the slice of this 3D object through the plane of the board, and then just draw some what are supposed to be circles but seen edge on. And usually if you can try to dot the parts that are going to be in the back, it's going to look better. Here, if I'm looking at it like slightly from the right, I don't need to dot these guys, because I would actually see the whole thing. Doesn't really matter. Okay, so that's basically how I drew this in the first place. Okay, so you can definitely draw that 3D object. The main thing we're going to analyze, though, we're going to use that 2D picture almost exclusively to get the 3D answer, which is really useful. Okay, finally, after all that pictorial setup, well, we're going to definitely need to do some more algebra here with these numbers, but let me just go ahead and start the process. The whole is the sum of its parts. That's how you should start every volume problem. Almost ever, as long as you're using calculus in any way, shape, or form. And then, not always, but for all the slicing stuff, it's going to be some cross-sectional area indexed by some variable times the thickness, which is going to be a small infinitesimal change in that variable. Here, the way we've done it, we've revolved something around the x-axis, so our individual slices are going to be, like a random slice is going to be something like this, same kind of deal. It's going to be an annulus, a ring shape, or a washer, seen edge on. If I want to emphasize the thickness, I could draw this. There's our thickness dx. But the main thing is the cross-sectional area, and that is going to be something, if you see it face on, is just going to be like this. It's going to have an inner radius and an outer radius. You can't see that very well. Little r and big R, but you'll see them here in a minute. Okay, but for right now, the main thing is x is the variable that labels the slices, dx is the thickness of a slice, and so we're in our somewhat of a home base, integral ax dx. Okay, then what is the area of a washer kind of shape? An annulus, a ring, just a circle with a circle taken out. That's just going to be the area of the big circle minus the area of the small circle. Now notice, big R and little r, those aren't x's. A big part of the setup here is translating what is big R depending on the x value. These are all different slices with different cross-sectional areas, and what is little r as a function of x. So these are functions of x still, but we're just making things progressively more explicit one step at a time. Here we just said we're using calculus, we're using slicing. Each slice is a washer, and I'm just going to go ahead and factor that pi out. And in fact, I could even take the pi out in front. Okay. And we're going to need to know the limits as well. Okay, and we're going to use a little symmetry there too. Okay, so what can I, okay, as usual, I can delete the title. Okay, so let's do a little bit more of the setup before we hit the big R and little r head on. Okay, that's going to be, okay, first of all, this thing is completely symmetrical around the x equals 0. That's by intention. I didn't have any coordinates that had to be used for this napkin ring, but I want it to be symmetrical around this plane in the middle, and so I just chose it to draw it symmetrically around x equals 0. That's great. So I can just take everything from 0 up to 20 in x and double it. So this 2 is a symmetry factor. It's not because of like a 2 pi from like circumference or something. Okay, 0 to 20. Okay, so that's some progress, but I still need to know formulas for big R and little r. Once I do, that's the end of the setup, and I just have some integral that I just, it's going to be just polynomials. It shouldn't be too bad. Okay, so what are those formulas? So that's where we go back to the cross-section. It really, you could even, and sometimes I encourage people to just kind of save a copy of this picture, the part that didn't have any of the rotation to it, and just says, hey, here's our big R as a function of x. That's one y value here. And there's a little r as a function of x. Because these guys are just straight around the x-axis, we'll do maybe an offset axis example eventually. That's going to get a little complicated. Those are just, the radius values are just coming from how far you were from the axis. In 2 dimensions, that is simply, I'm getting all these notifications, sorry. That is simply the y value of this curve. Okay, so we need a parabola. So let's do the outer one first. That is a parabola that starts out at 20 when x equals 0 and gets a little lower. So it's going to be minus something squared. And it's not too hard to figure out. Let's see. We want, when x is equal to 20, if I take 20 minus x over 20 squared, that'll take it down by 1. Ooh, I wanted to go from 20 to 18. 20 minus 2. Aha. Okay, so that's that big R. And then that's all squared. Ooh, careful. So the fact that I have this little square is because I just am using a parabolic curve to design this thing. It didn't have to be. You could use a sort of part of a circle or something like that. But just for simplicity of the algebra, I'm going to try and use a parabolic curve. This square is from the geometry, from the fact that we're talking about the area of a circle when we actually do the rotation. Okay, minus, now 15. This is a parabola that's going ever so slightly up. That's 15 plus, again, when x gets to 20, I want to go up just 1, so it's really 15 plus x over 20 squared. Okay, So that's a part of the process, getting these formulas, these quadratics, that is its own thing. I skipped over that pretty quickly. Most of the time in a book problem, you're going to be given these formulas. But I wanted to show you something where we really just had some measurements, and then simply let's use parabolas to do that. And then with a little bit of algebra and sort of analytic geometry, you can figure out what these formulas have to be. But you could also imagine, suppose somebody actually just gave you these as the big R and little r. Okay, so now that is going to simplify. Let's see, I'm going to leave this, but I don't really need the qualitative picture anymore. Okay, and let's see, there's some, this is something where you don't absolutely have to do a U sub. You could totally do it without a U sub, but it's a great place for a U sub. What I often call a convenience U sub. This is going to be, let's say, let U equals x over 20, because this just creates some annoying fractions. Then du is dx over 20, or dx is 20 du. Ooh, that's right at the edge of our little screen. Sorry. Let me put it over here. Dx is 20 du. Okay. And let's see, if x goes from 0 to 20, u conveniently just goes from 0 to 1. That's really nice. Okay. So basically what I'm using is that 20 is a natural scale for this problem, and this basically just changes the units from millimeters to units of 20 millimeters. And that actually is very nice. Okay, so now the dx is 20 du. Oh, that's going to come out here. So that's going to create a 40 pi. And now I'm just going to rewrite this in terms of u squared. Still have to deal with this the squares of these quadratics, but it's not too bad. 15 plus u squared. Ooh, I forgot a square here. Ooh, wonder if anybody noticed that. Right, so this was the r value, and that's the square, and I just totally forgot that. Squared, boom, and then du. Okay, groovy. Okay, and so now the rest of it's not particularly super interesting, but we just have to work out the algebra. So we're going to get 400 minus 2 times 20 times 2 minus 80 u squared plus 4u to the 4th minus 225 minus, this minus is going to distribute, watch out for that, 30u squared, and then minus another u to the 4th, all du, 40 pi. We're just going to collect. So we're going to get 175 minus 110 u squared plus 3u to the 4th du, 40 pi, 175u minus 110 over 3u cubed plus 3/5 u to the 5th from 0 to 1. And luckily 0 to 1 is the easiest to ever do for polynomials, because it dies when u equals 0, and then just everything becomes 1 when it doesn't. So 40 pi times, kind of a funky fraction still, 175 minus 110 thirds plus 3/5. Notice this part is really minor. That last little u to the 5th has a very small contribution. So that's about 30-ish. It's going to be about 140 times 40 pi if you simplify it and get a fraction. But I think we're done.